Welcome everybody to Integrated Math 3. In today's episode, we're going to be discussing Chapter 9.1.5, which is the unit circle with radians. Now, radians is going to be a really important type of measure that we're going to learn and employ almost exclusively as we move forward. Radians effectively are a different way to measure an angle. So the question would be, why would we need radians if we already have degrees? Well, the idea of degrees, if we look at a circle, because we've learned for so long that a circle has 360 total degrees, we've just come to accept it as a part of as just a fundamental truth. Well, unfortunately, that's true only because of where we live. When 360 degrees was developed, it was developed as a means to understand one cycle. 365 days are in a year, but that's really hard to divide by a bunch of different numbers. So when math was beginning to be developed, it became 360 because then you could divide that by 180, 90, 45. Lots of different numbers could divide easily into 360, and it basically encompassed the idea of one cycle. If you had about 1 year would be about 360 days. I know it's 365, but you could reasonably predict one cycle or one period of some type of periodic behavior like seasons or all that stuff. Radians, on the other hand, are a type of angle that is inherent to circles. So, in order to illustrate what radians are, I'm going to kind of delve into a small little story here. And that story begins with the ancient Greeks tying people up to ropes and making them run in circles. And so what happened was the person, let's go and call them, let's call them Mags. We tie up Mags to a rope and we make her run a certain amount of distance. Now, let's just pretend that the rope's radius or the rope's length is 5, and that is what would comprise the radius of this circle. Well, Mags, what we had her do back in the ancient Greek times was run a distance of 5, let's say 5 units. So she ran 5 units of arc length. And because the 5 units of arc length and the 5 units of the radius were equal, when we had an angle that was based on the length of the radius and the arc length being the same, this angle created was called 1 radian. And I'll go and type in that definition for you. A radian is an angle created when the arc length and radius of the circle are equal. And so what happens with radians is that they are inherent to all circles. So if we were to make the circle, say, smaller, and we were to have, say, altruistic run let's call this thing 1 unit now, he would only have to run 1 unit of arc length to create 1 radian. Because all circles are similar, their scale factors would all be the same. You'd have to either run a longer distance on a longer radius or a shorter distance on a shorter radius, but no matter what, the radius equaling the arc length when run in that circle creates 1 radian. And so what happened was the ancient Greeks, they ended up having the ancient Greek versions of Mags and Al run 1 more and then 2 more radians. And I'm going to go and demonstrate this in Desmos real quick. Let me go and go to Desmos real quick. So we have our circle here in Desmos. And right now, we're at 0 radians. This black circle here, this black open circle where it says 0 radians, that is where Mags or Al is. And so what happens is that if I run 1 radian, I'm here. 2 radians, I'm here. 3 radians, I'm here. Now, the idea of this is that, unfortunately, as frustrating as it is, 3 radians stopped shy of going halfway around the circle. And as we just discussed, we have all circles being similar, which means no matter how much you shrink or grow the circle, when you run 3 radians, you are always going to stop just shy of halfway. So, how did the ancient Greeks deal with this eventuality? Well, what they did was they had a circle, and they had the person run halfway through. So if this is 0, because this halfway marker was so close to 3, they had to think of a number that was really close to 3 and just a little bit above it to identify this value right here. I'll give you a second to think about it, and you might already know what number that is. And if you guessed the number pi, then you guessed correctly. And I'll give you guys a second to, if you have this resource page on you with this unit circle on it, go ahead and draw 0 and pi. Now what I'm going to do next is I'm going to go ahead and call this 12 pi over 12. And what we're going to do is we're going to go through and we're going to actually draw all of these dots here. Now this should look familiar. This is the same circle that we used from the Screamer. I'm going to go and draw every single angle measure all the way across. So that's going to be up here, 6 pi over 12. And then this is going to be pi over 12, 2 pi over 12, 3, oh, that's not visible at all. I'll switch to red. 3 pi over 12, 4 pi over 12, and 5 pi over 12. So I apologize for the half ketchup, half mustard effect here, but we're just going to keep on going. So 7 pi over 12, 8 pi over 12, and so on. I'm actually going to go and pause, and then we'll go ahead and come back when all of the radian angles are drawn in. Give me a second. And we are back with every single radian from 0 to 24 pi over 12 drawn on this unit circle or the Screamer, depending on how you want to look at it. Now, I'm going to draw analogies back to the Screamer. Remember when the Screamer happened, right? I said that we were going to ignore the 15 degrees, the 75 degrees, the 105 degrees, because they didn't create special right triangles. Well, if you look at the Screamer and you have your equivalent values here, that means I'm going to eliminate the 15 degree angle. That's in the same position as the pi over 12. I'm going to eliminate all of those types of angles that we weren't able to utilize special right triangles for. And I'm just going to get rid of them, and I want you to do the same. Now, what I want you to notice here is that all these angles here that I just eliminated, not only are they in the same place with the degrees that didn't create special right triangles, they also belong to radian measures that can't be reduced, right? I can't reduce pi over 12. I can't reduce 5 pi over 12, but I can reduce 2 pi, 3 pi, and 4 pi all over 12. I can reduce these 3 guys in the middle. I can reduce these 3 guys in the middle and these 3 guys in the middle in all the other quadrants. So there's a reason for that. And so what we're going to do now is I'm going to have you guys pause, and I'm going to pause also. We're going to draw another circle with everything reduced. Okay, I'll be right back. And we're back now with everything being reduced. And so, except for a 24 pi over 12. Whoops, totally forgot about 2 pi right there. Okay, so I've cleaned it up. We went from here, this is before, 2 pi over 12. If you notice, the 2 pi over 12, which was in yellow, has now become 1 pi over 6. Pi over 4, pi over 3, pi over 2. These are all angle measures in radians now. We are now leaving degrees, right? We are now in radian mode. And so from here, hopefully, a lot of this stuff is going to make sense because we're just going to do equivalent statements. Now, back when we did the Screamer, we had a right triangle here. That was 30 degrees. And I asked you to find 2 things. Remember, the Screamer had an arm length of 1. We were trying to find the height, and we were trying to find the lateral distance from the center. That was in the last video. Well, remember, this y here was equal to 1/2, and that x value was equal to rad 3 over 2, creating coordinates of rad 3 over 2, comma 1/2. Well, from here, for now, just until the end of this video, I hope you can trust me that because the 30 degrees and the pi over 6 are in the same position, they are equivalent angle measures, and I'll prove this to you at the end of this video. Same idea. The next triangle here, was 45 degrees. Well, I'll give you a hint as to where 45 degrees happens. Let me get these measurements in, rad 2 over 2. 45 degrees Well, that's the same value as pi over 4. It's in the same position. And again, that leads me to believe that 45 degrees is equivalent to pi over 4. And again, I will prove this to you. Maybe not at the end of the video, maybe after these examples. And then I'm going to go ahead and do the 60-degree angle, the 60-degree triangle. So that's going to be 60. We saw this as rad 3 over 2 and as 1/2, meaning your coordinates that were in the same position, wrong color, would be 1/2 comma rad 3 over 2. And again, that leads me to believe, because they're in the same position, 60 degrees is equivalent to pi over 3. Okay, so before I prove that these angle measures are equivalent, let's go ahead and hit the pause button again. We will fill in every single radian measure on this unit circle right here. I'll be right back. And here we are with a completed unit circle with all of the various side length measures of every special triangle that is in trigonometry, a special right triangle, with all of their corresponding radian measures and all of the correct negatives and positives in place. So I hope you paused. That way you could put in those values before I did. But again, what did we do? We just got the first quadrant, and then we looked for symmetric buddies like we always have, because a circle is symmetrical. And there it is. That is the unit circle with radians. And a couple things before we take off. One, let's go ahead and show that these values are actually equal. So what I'm going to do is I'm going to take a degree to radian measure that's really easy. I'm hoping that everyone can agree that 180 degrees is equal to pi radians. Oops, this is degrees. So if I wanted to convert from 30 degrees to radians, I would say 30 degrees, hopefully this makes sense from science, and I'm going to say multiplied, I'm going to go ahead and say 180 degrees, because I want the degrees to be able to cancel each other out, over pi radians. The degrees cancel, the zeros cancel. I end up with 3 pi over 18 radians. Those guys can kind of cancel. I end up with pi over 6 radians. And what do you know? We assumed 30 degrees was pi over 6 radians, and it actually was. You would use the same technique for 45 and 60. And there you have it. That is the unit circle in radians. Now, what I didn't speak about is why radians even matter. Why would we even need radians when we have something in degrees? Well, remember, a radian is an angle created when the arc length and radius of a circle are equal. So this inherently creates an easy transition and an easy conversion from angular motion to linear motion, which degrees cannot do, because degrees are an artificial construct because of how we are as a species. When you have radians, which are inherent to radius and arc length being the same, that allows you to figure out how fast a wheel might be spinning and how much distance it's covering, for example. Anytime you're dealing with a problem that deals with angular to linear motion, radians is going to be how you proceed with that problem. So that is the advantage to learning radians. We will be working almost exclusively in radians throughout trigonometry. So hopefully this makes sense to you. As always, please leave comments or questions in the comments area. I will see you all in the next episode.